Today we're going to be looking at the infinite geometric sum. And rather than just tell you what it is, I'd like to help derive it for you and do a little experiment so that maybe you can come to see why the infinite sum works the way it does on an infinite geometric series. So we're going to start with a square piece of paper. And mine happens to be this orange one. And we're going to take that piece of paper and we're going to cut it in half. And then we will take one of those halves and we'll place it on the desktop or white space over here. So according to this table, it says what is the area of the piece with respect to your original square. So this is half of my original square. Then write that as a decimal would be 0.5. So here in my white space, my desktop space, I have an area of 0.5 total. Then we're going to take the square and cut it in half again. And place that half on the desktop. So I had a half that I halved again. So half of a half is a fourth, which is 0.25. I had 1/2 plus 0.25 gives me a total area of 0.75 over here on my desktop. Then I'm going to take and cut my square in half again. So half of a fourth is an eighth, which is 0.125. And I'm going to take that eighth and add it to my desktop. So now I have added 0.125 to 0.75. So I should now have 0.875 over here in my white space. Then it says to make another cut. So I'm going to cut this one more time. And take that half of an eighth, which is 1/16. And a decimal of 1/16 is 0.0625 that I have added to my desktop of 0.875. So I now have 0.9375. Then I'm going to make one more cut. So I have half of a 16th, which is a 32nd, which in decimal form is 0.03125. And I'm going to take that half and add it to my desktop of 0.9375. And I now have a total of 0.96875 over here in my space. And then I'm going to make one last cut. In half. And take that half and add it to my desktop. So half of a 32nd is 1/64th, which as a decimal is 0.15625, and I've taken that and added it to the rest, which was 0.96875. And I have 0.984375. And if I continued this process forever and ever, I would be adding n pieces. So continue to cut in half and half and half. And I would eventually end up doing what to my original square? the total space over here should approach the space of that original square. So my total combined area should be getting closer to the whole space, 1. Are my numbers continually getting closer and closer and closer to 1? And yes, they are. So what we could do there is say that by me continually adding, which is what a series does, and when I'm finding a sum, I'm continually adding all these together, that space can never get bigger than the original 1 that I had. And that idea is called mathematical convergence. When a sum approaches a number, we call that convergence. And according to ours, we kept approaching 1. So if you recall, the sum of a geometric series was a sub 1 times 1 minus r to the n over 1 minus r. We're going to take this idea and see what happens when I say, what if I continue doing it forever to infinity instead of just to n? And by doing that, we are actually going to be examining this part of the formula, 1 minus r to the n. And we want to see how that relates to our experiment of continually adding on half, 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 half. So to do that, we're going to use our graphing calculator. And I need to shrink here so we can see that. There we go. And on our graphing calculator, we are examining 1 minus r to the nth. And in our case, from term to term to term, we kept multiplying by a half, multiplying by a half, multiplying by a half, multiplying by a half, multiplying by a half. So my ratio was 1/2. So I'm going to put that here in the calculator, which I've changed to sequence mode. 1 minus 1/2, which is 0.5, raised to the n. And if we start at 1 and look at our table, let's see what that 1 minus a ratio to the n approaches. Look at these values. They kept getting closer and closer to what value? They're getting closer and closer to 1. Let's see if I keep going, if they actually do get there. There they are. That's the closest they can ever get, is to 1. So that does model our original experiment, because our sum kept getting closer and closer to 1 too. And now we've discovered that 1 minus r to the n is also getting closer and closer to 1. So what we can do is take this 1 and substitute it into this equation, which would give us a sub 1 times, we're replacing this part with 1 over 1 minus r, which if I multiply that out is just a sub 1 over 1 minus r. That's how I get to an infinite sum. And we've just proved it, because as I kept heading further and further and further down the road, closer to infinity, 1 minus r to the n converges to 1. So now, let's see if that formula will work for every single ratio that I have in an infinite sum. Right now, my denominator here says 1 minus r, and my denominators on a fraction cannot equal 0. So if I add r to both sides, I would get 1 cannot equal r. So far, I can never have a ratio of 1 down there, or my infinite sum will not work. Let's see if there are any other ratios besides 1 that won't work. This one says our calculated formula, which was a sub 1 over 1 minus r. I'm going to shrink this back down. Let's see what we get in this case. So from term to term here in this series, 1 to 2/3, I multiplied by 2/3. 2/3 to 4/9, I multiplied by 2/3. 4/9 to 8/7, I multiplied by 2/3. So that makes my ratio 2/3. Let's use this formula to see what that sum should converge to. So I have my first term is 1 divided by 1 minus my ratio, which was 2/3, which is 1. 1 minus 2/3 is 1/3. 1 divided by 1/3 is 3. Well, let's put that over here in our calculator and see if we still get a sum of 3. So our first term was 1 times my ratio, 1 minus 2/3 raised to the n divided by 1 minus 2/3. And let's look at our table and see what it approaches. As my n's keep getting bigger, what number is my sum approaching? What is it converging to? And it's looking like 3 to me. Let's see if we keep going, if it actually gets there. There it is. We do actually get to 3. So by using the calculator, we also do get to 3. So it's looking like our formula is working. When our ratio is 2/3, we did still get our formula to work. Let's try this second series. 1 plus 3 plus 9 plus 27. From term to term to term, I'm multiplying by 3. So my ratio is 3. So again, using my formula, my first term is 1 divided by 1 minus my ratio of 3. That's 1 divided by a negative 2, which would end up being a negative 1/2. Let's see if when I actually calculate it with my old formula, I get that. So instead of a 2/3, I need to change this to a 3. Let's check our table. Oh my, we have these big numbers. Let's go back to 1 and see what's occurring. Is my sum converging? Well, it just seems to be growing bigger and bigger and bigger and bigger. So my sum does not converge. It keeps getting bigger, so it keeps getting closer to infinity. So will my formula work when my ratio is 3? Do these two match each other? No. So what that means is I now have a few more restrictions on my original formula. Not only can the ratio not be 1, but how does 3 compare to that? How does 2/3 compare to that? That's right, the ratio has to be less than 1. So we are going to say the absolute value of the ratio, so it doesn't matter if it's negative or positive, has to be less than 1. Then my formula I generated will always work. So whenever you have a geometric infinite series and you are supposed to add it all up, it means, again, that the sum will always be the first term divided by 1 minus the ratio, as long as the ratio is less than, or equal to 1. Now let's use that. And I won't need my calculator more, so we'll go bigger. Here I have an infinite geometric series because it goes to infinity. My ratio is 0.1. So is 0.1 less than 1? Yes, it is. So I will have an infinite sum. So I take my first term divided by 1 minus my ratio. My first term, if I put 1 in here, 1 minus 1 is 0. 0.1 to the 0 is 1. Times 2 is 2. So my first term is 2. Divided by 1 minus my ratio, which was 0.1. And I get 2 divided by 0.9. And I can never have a decimal left in a fraction. So I have to move that one place. So I must move this decimal one place. And I get 20/9. So that sum will converge to 20/9. Let's try the next one. I still end up having an infinite sum because this series never ends. But I didn't write it using sigma notation. I just wrote it using my plus signs. So let's see what the ratio is from term to term to term. From 12 to 1/4, I multiply by 1/3. From 4 to 4/3, I multiply by 1/3. From 4/3 to 4/9, I multiply by 1/3. So my ratio is 1/3. Is 1/3 less than 1? Yes, it is. So we can use our infinite sum formula, which says first term, which was 12, divided by 1 minus my ratio, which was 1/3. So this becomes 12 divided by 2/3, which means 12 times dividing by a fraction is the same as multiplying by its reciprocal. So that would be 3/2. And this reduces to 6 times 3. 18 would be my infinite sum here. Let's try a few more. They're telling you an infinite geometric series has a first term of 5. And the sum, so the sum of the infinite series is 27/5. So knowing the formula, an infinite sum equals the first term times 1 minus the ratio. In place of the infinite sum, I can put 27/5 equals the first term, 5, divided by 1 minus the ratio. Now, I should be able to do cross products. 5 times 5 will give me 25 equals 27 times the quantity 1 minus r, which is 25 equals 27 minus 27r. Subtract 27. Negative 2 equals negative 27r. Divide by negative 27. And I get 2 27ths as my ratio. Let's see how we can use an infinite series to write a fraction. from a repeating decimal. On this repeating decimal, if I rewrite it, it starts to repeat right here. So I would write the first 3 digits, because that's not repeating, plus, and for some of you it might make more sense if I line it up, I would have to fill in these 3 places and then a 27 to get 02727. So then plus 00027 plus, now I have 5 places to fill in to get another 27 plus that continual pattern. So is this an infinite series? Yes, it is. And if I want the sum of an infinite series, I take the first term, which is 0.027, over 1 minus the ratio. To find my ratio, I take this divided by this, or in other words, I added how many decimal places? I had the original 3 and added 2 more. So I had always added times 0.01 times 0.01. So my ratio is 0.01. So this is 0.027 over 0.99. And again, I can't have decimals in there, so I move this 3 places, so I must move this 3 places. So that becomes 27 over 990. And 9 goes into both those. 9 goes into 27 3 times. 9 goes into 990 110 times. So that sum should reduce and converge to 3 over 110, which means 0.027727272727 will be equivalent to the fraction 3 over 110. Let's try another one. Here's where it starts to repeat at those 6's. So I write down the first part. 0.041 plus, I need to fill in 3 decimals, 6, plus 4 decimals, 6, plus 5 decimals, 6, plus, etc. Is my series infinite? But the repeating pattern does not occur until this point. So we're just going to rewrite this part as a fraction, 41 over 1,000, plus this is where the repeating starts. So where the repeating starts is where I have an infinite series. So my first term, 0.0006 divided by 1 minus my ratio. Every time I added 1 more place in there. So that would be times 1/10, times 1/10, times 1/10. So 0.1. 0.0006 over 0.9. 1, 2, 3, 4 places. 1, 2, 3, 4 places. Becomes 6 over 9,000. And that reduces. Actually, let's leave it to 6 over 9,000 because I have to add that to my 41 over 1,000 plus 6 over 9,000. So if I multiply both of these by 9, I will have them in 9,000s. That gives me 369 over 9,000 plus 6 over 9,000, which is 375 over 9,000, which simplifies to 1 over 24. And one last problem. A pendulum swings 10 feet going from left to right. On its swing back, it swings 90% as far as the first swing. On each successive swing, it is 90% of the previous swing. We are to find the total distance. So let's see what's happening. I'm starting with 10, and then my next time I go 90% as far, and then my next time I go 90% as far, and my next time, etc. So my ratio, every time I'm multiplying by 0.9. So is this an infinite sum? Yes, it is. So the sum would be the first term, which was 10, divided by 1 minus the ratio, which is 0.9. 10 divided by 0.1, move one place. 10, 100 divided by 1. My sum will converge to 100 feet that the pendulum will reach in its consecutive swings. Now you should be able to try some problems on your own.